There was a change in the program as announced from Oxford University. Stephen Blundell kindly take this summary talk. So please take it away.
Thank you very much, and thank you very much to everybody for staying for the final bit and of this extremely interesting day. It's a great pleasure to be here, and I'm standing in for Patricia Farrer, and I hope she gets well soon. So we've had a great day looking at feuds throughout history, and we've seen various different characters. I've got a few of them here on this slide. Of course, the Greeks, we don't really know what they look like, so we have just our ways of imagining them. Parmenides, we were hearing today that the only thing that exists is a sphere, so I thought the only way of drawing Parmenides was like this. Thank you. Similarly, Hooke, we have a lot of questions about what he actually looked like, because essentially all his portraits were destroyed, and maybe one that survives is possibly him. So he's known for his spring law, so I've had to improvise with that one. But the others, I think, are genuine pictures or paintings. So what have we seen today? Well, we've seen some very important myth busting. So Professor Anne-Marie Roux showed us that the idea that Galileo was essentially standing up for truth against the Catholic Church, who were persecuting him for having come up with heliocentrism, was a gross oversimplification. And that this combination of Galileo's personality and the way he went about that particular controversy was essentially what caused him to be tried by the Catholic Church. And the story we're often told is much more complex. We were also I think reminded by Andy Gregory. He did a very good job, I think, of persuading us that some of these long dead ideas associated with some Greek thinkers, that nothing does not exist and the only thing that does exist is spherical. You could kind of see the logic, and the way he drew out the fact that atomism was rebelling against that and saying that if you just alter the one proposition that the nothing can exist, then you end up with these, as he called them, Parmenidean atoms, these individual spheres that exist with nothing in between them. This idea of atomism was generated. He also, of course, explained this idea of Plato's triangles making up the world and making up all of the solids. And we heard about the connection between that, I think, in one of the questions, and string theory. Both of these are ideas that are pursued because of their mathematical simplicity. Neither Plato's triangles or strings theory are supported by any experimental evidence at all, so there is some potential similarity there. And then Rob Iliff showed us how Newton wanted absolute certainty. He hated hypotheses, he detested feuds, but his very nature led him into incredibly destructive feuds. And his ideas were decried by Leibniz as spectres of the imagination. And you think that must have hurt, given that he thought he was the one that didn't need hypotheses. He was working with absolute certainty and real truth. And then Richard Werner reminded us of the complementarity of truth and clarity, and perhaps demonstrated that Bohr showed you could be in a state of both total lack of clarity and yet not have found truth. And then finally, Simon Mitten described a feud which was about something incredibly significant, the very nature of the universe. What was at stake? Does it have a beginning? Does it have a finite or infinite age? And actually, he reminded me of this point that many of the early radio astronomers had come from the war working on radar work. And in fact, those people who were working on microwaves and radar, some of them here in Oxford founded electron paramagnetic resonance, and essentially turned that radar technology into looking at the micro world and condensed matter physics, my own field. In Cambridge, they turned them to the heavens, but they were amateurs, they weren't astronomers. And his talk reminded me of a talk I'd been to by F. Graham Smith, who pointed out in those early days when these non-astronomers didn't really know what they were doing, they built this radio telescope, their very first one, in a field in Cambridge, and it was a bit of a surprise to them after they built this thing and mounted it, that with radio telescopes you should really line them up with the ecliptic so that as the heavens rotate you can measure the signals. They'd lined it up with the hedge of the field, and it was perfectly parallel to the hedge of the field, but strangely that hedge was not aligned with any celestial coordinates. This is something that hadn't occurred to them. So I thought in this brief summary talk, what I might do is just bring a few things up to date and draw some of these threads together. So we heard about the ideas of atomism in the Greeks, and of course they were pitted, ideas of atoms were pitted against Aristotle and Plato. And in the early modern period, of course, it was Aristotle and Platonic thinking which was dominant and had become essentially entangled and conflated with Christian thinking. And so, therefore, one of the problems with atomism was that it was mixed up with these terrible Epicureans who'd been after pleasure and wanting to fill their lives with pleasure, and this was definitely against the direction you wanted to go in. So, in fact, it was Pierre Gassendi, a clergyman, who essentially Christianized atomism and found ways of reinterpreting that and realizing that you didn't actually have to reject Christian thinking in order to embrace the existence of atoms. Then it was people like Torricelli, and here in Oxford I have to mention Robert Boyle, who were working with vacuum pumps and actually making the void, actually making vacuums in their laboratories just along the high street here in Oxford, essentially founding chemistry, kinetic theory. Boyle was an experimentalist and somebody who embraced that kind of atomic thinking. So it started to come back into fashion. And it's amazing how late these ideas were still being debated. So around the turn of the 19th century, you have John Dalton in Manchester asking questions, as you can see in this quote here, about what's the nature of chemical reactions, and trying to understand how atomic weight and the way in which chemical reactions combine can be explained through an atomic hypothesis. And Dalton came up with his ideas saying essentially all matter is composed of atoms. All atoms of a given element, they're identical to each other. They have the same mass, charge, chemical properties. Atoms can't be created or destroyed. What you can do is combine them together in whole number ratios to make compounds. And therefore you can interpret this idea of chemistry in terms of the existence of atoms. You can't see atoms, but you can hypothesize them and you can do calculations and it works. So essentially what Dalton was doing was sort of giving us our modern understanding of things like water being H2O, two atoms of hydrogen and one of oxygen combined together in a molecule. And here you can see in a molecular diagram. But it's amazing how late the resistance to the atomic ideas goes. So you have somebody like Berthelot, who asked the question, well, did anyone ever see a gas molecule or an atom? It's all very well having this atomic hypothesis, but you can't see them. So can you really be sure that they're there? And he points out that chemical symbols, you may use them to try and do calculations about chemical reactions, but they're dangerously subjective. The algebra of combinations is appealing, and of course the human mind is naturally inclined to substitute for a direct conception of things, which is invariably lacking, a simpler view in terms of descriptive symbols that, and my bold here, that give the appearance of more completeness. In other words, this is a way you can calculate things, but it doesn't really correspond to reality. That would be going beyond where we are. Wilhelm Ostwald, these are all great scientists who did wonderful things in their respective fields. Ostwald, we developed the theory of Ostwald ripening, which is very important in material science, and various other things. But here you can see him saying atomism is a doctrine that has miserably failed in any serious attempt to explain through mechanism all known physical phenomena. It's even less likely to succeed in tackling the incomparably more complex phenomena of organic life. And of course, we can laugh at that statement, as we know that DNA, we know its atomic structure, and this was one of the great triumphs of the 20th century. And it was people like Ostwald that gave this man a hard time, Ludwig Boltzmann. Ludwig Boltzmann was developing a theory of thermodynamics that had been developed in the late 18th and early 19th century and through the 19th century in terms of a thermodynamical theory that didn't make any hypothesis about atoms. It just looked at things like pressure and volume and temperature, looked at the relations between them, tried to understand thermodynamic systems, introduced ideas like energy and entropy. And Ludwig Boltzmann was trying to put it onto a statistical formulation, a way of understanding what might be going on at the microscopic level, which was consistent with thermodynamics. And he was developing the subject we now know as statistical mechanics. And one of the tenets of that theory is that atoms do exist. There is a microstructure underneath these thermodynamic systems. They really do exist in terms of atoms. And Ludwig Boltzmann got it in the neck from people like Ostwald and various other Feuds as well with Mach. And eventually he committed suicide, I don't think primarily because of the attacks that he was getting, but they can't have helped. You can even find in a chemistry textbook in 1902 by Pure Duhem, and this is after a lot of evidence for the existence of atoms have come, not only from chemical reactions, but all kinds of things like the work of Avogadro. So here in a chemistry textbook, and again, another great scientist, Pierre Duhem, we know him from the Gibbs-Duhem relations in thermodynamics. Upon noting that the ease and clarity with which all principles of modern chemistry fall into place in a treatment, excluding the name and notion of atom, one cannot help but think that the unique success of the theory of atoms is an illusory victory without future. And then, all things considered, modern chemistry does not support Epicurean doctrines. So it's incredible how late this is, that people are right in the dawn of the atomic age where radioactivity has been discovered. The quantum theory is just on the cusp of appearing. You have people railing against these notions. Now, it's often said that science advances one funeral at a time, and that therefore you need a generation of people to die off. But it's interesting how some of these ideas come round. So let's take this idea of the void that we've heard about so much today. One of the questions was, does it exist? And the Greeks were arguing over this, and Torricelli and Boyle, etc., say yes, they can make the void, they can make vacuums in experiments, and they can produce a volume of gas inside a glass vessel where they pumped all of the air out. In fact, their vacuums were not that great, but we now know, of course, you can make fantastic quality vacuums. But there was also this nagging question that we've heard alluded to in various talks today, how actually does Newton's law of gravitation work? Here was this amazing scientist that we heard about from Rob Iliff, difficult human being, but somebody who'd made extraordinary strides. He had this inverse law, a square law of gravity, that he argued over the priority of with Hooke, although Hooke essentially had just guessed a hypothesis. He'd shown how it was consistent with Keplerian notions. But how does it work? Because essentially all mechanisms in the 17th and 18th century all worked essentially on clockwork. You had to know how the mechanisms worked, how the gears fitted together, because we were living in a clockwork universe. And the kinetic theory of gases worked this way. Why is it you have pressure? Well, it's because of molecules bouncing off walls. You could develop that kind of theory. But how do you get action at a distance? How can the motion of the Earth and the Moon affect each other when they're separated by nothing? Where are the gears and where are the wheels? And so this is an interesting question about the void. Science apparently showed that the void exists. Of course, the modern view is we've almost gone back the other way, and we say actually the vacuum is teeming with activity. What you think of as empty space actually contains a soup of virtual particles coming in and out of existence. Forces are actually mediated by the exchange of virtual particles. So in a funny kind of way, we've wound things back and have said that the vacuum is more complicated than we thought. So it's interesting to see how these century, maybe even millennium-old debates are still continuing. Well, we've heard a lot today about feuds, and what essentially have these feuds been due to? Well, I think you can identify two main sources. There have been questions of ideas, really asking deep questions about physics. Did the universe have a beginning? Sorry, the university. Freudian slip. Is the universe, or indeed the university, made of atoms? And then, of course, questions of priority. Who got there first? Whose name should be associated with a particular discovery? And, of course, you can see that these things are a strong function of personality type. Particular individuals in the history of science, as we've seen today, have become enormously sensitive about questions of priority, partly because it's bound up with the whole notion of who they are as people. And of course, because we've been doing the history of science and looking over that period, we've been doing a history of course, European white men. And I guess here perhaps the men is the most important thing. There have been a number of very big egos. So I kind of wanted to close today by just looking at a couple of examples of cases where it goes in the opposite direction. So one example we've heard a bit about today is Paul Dirac. Dirac was a complex man, in some ways a complex personality type, just like Newton, but in his case it produced a very different type of behavior. Yes, he was a highly individualistic thinker, somebody who was very much in his own world, someone who found it, like Newton, rather difficult to relate to other people. But in Dirac's case, he was not hostile and he was not disputatious. He was somebody who was actually very anxious to give other people credit. And just one example out of many. So I showed this facsimile of this quantum mechanics textbook from 1930, one of the first major quantum mechanics textbooks, not the first, but the most influential. And much of our language, the way we teach quantum mechanics today, is based on Dirac's terminology and the way he brought things together. One of the things he mentions in this book is this idea that had been developed only in the last few years at the time of all particles in nature being either fermions or bosons. Fermions are things like electrons and protons and neutrons. Bosons are things like photons, and we would also say the graviton and the recently discovered Higgs boson. And so everything in nature is one or the other. Now, the distinction between these two types of particles is the way in which they occupy quantum states. Fermions are gregarious. You can put lots of them in a quantum state. Bosons are a little bit like Newton and Dirac. Only one of them will go in a quantum state. And the statistics that they show, which means the way they distribute themselves around quantum states, is due to some theories developed essentially independently by Enrico Fermi and Paul Dirac for fermions, and Bose and Einstein for the bosons. And Dirac was the one who coined the term fermion and boson, and it's notable that he gives the credit to Fermi, even though Fermi and Dirac were working in one sense independently, but he gives Fermi the credit, and he gives Bose the credit for the bosons. And that's very typical of him. He refers to what we would call the Dirac delta function in his book. He, of course, refers to it as the delta function. And not all scientists behave in that way. Well, going back a bit in time, we've heard a little bit about Sir Christopher Wren. I wanted to mention him for two reasons. One is that he died 300 years ago today. So this is actually the anniversary of his death today. As Rob reminded us, it rather depends a little bit on which calendar you use, but on one of those calendars, if you use the calendar he would have used, it was February the 25th. So this is indeed the 300th anniversary of his death. He was the 9th Gresham Professor of Astronomy, and I'm married to the 38th. So that's another reason of mentioning this. Now, Christopher Wren was, of course, knocking around with a lot of the people we've heard about today, and he came up in Rob's talk. Christopher Wren was born at a rather difficult time because it was in his teenage years that the Civil War was raging. He was the son of the Dean of Windsor, so he was very much on the royalist camp because essentially he'd grown up in Windsor, where his father had a good living. His uncle was a prominent bishop. When the Civil War started, his uncle was sent to the Tower and spent the Civil War in the Tower. His father lost his living. Wren was associated with the royalist side because of that family connection. And in 1660, at the Restoration, you have somebody whose life has very much been shaped by growing up in civil war, where everyone was against everyone else, and trying to rebuild a society where you have to navigate disputes without it leading to pistols at dawn, as it were. And so Christopher Wren is a rather interesting personality type because he is very different from both Hooke and Newton. He's somebody who seems to have most of the time got on with absolutely everybody. Even people like Hooke. He was a great friend of Hooke. Flamsteed, who Rob didn't have time to tell us very much about, somebody who was enormously secretive about his astronomical records, not willing to share them with Newton or anyone else. Christopher Wren was involved in designing the new Royal Observatory at Greenwich and having to have lots of dealings with Flamsteed and also interacting with him. Flamsteed talks about Wren in glowing terms, even though he didn't get on with other people very easily. So Wren seemed to be somebody who could navigate these choppy waters. And just a couple of examples. So although Wren is mainly, of course, known as an architect, he did a lot of science. And one of his early bits of science was working on Saturn. He did many observations here in Oxford and also from London, studied Saturn over many years. And the big question was, what were these ring structures? Of course, we all know about the rings of Saturn, but they were very poorly resolved on old-fashioned telescopes. And Wren came up with a theory of what this was, and this was essentially his first big scientific publication. He thought it was some halo around Saturn, around the planet Saturn. And the issue is, as you go through the year, Saturn shows different bits of its rings to us. Sometimes they're edge-on, so it looks like there's just a line, which you can barely see. At other times, the rings are tipped back, and you can see this halo more prominently, what was going on. Huygens had another theory, which was the right one. Huygens came up with the idea of a ring. Once Wren had seen Huygens' idea, he wrote, he was just convinced by Huygens' idea, its natural simplicity, and this was a contrivance agreeing so well with the physical causes of the heavenly bodies that I love the invention beyond my own. So, here's a testament to the man that he could abandon his own idea because he'd seen a better one produced by somebody else. There was a bit of an argument between Huygens and Wren, because Huygens was actually quite a difficult character, but once the two men had met, they seem to have got on reasonably well. And then, of course, we heard quite a lot about micrographia. This is a picture from Hooke's book, these amazing drawings. But it's interesting to note the preface of micrographia, because in fact it turned out that there could have been a dispute here, because the first person to do lots of drawings under a microscope was actually Christopher Wren. And in the preface to Micrographia, Hooke writes that he and of course it's the tradition of the day that you write a rather flowery preface, but he says he's reluctant to write this book because he was to follow the footsteps of so eminent a person as Dr. Wren, who was the first that attempted anything of this nature, whose original drafts do now make one of the ornaments of that great collection of rarities in the King's Closet. And then he goes on to say, Dr. Wren did affright me, for of him I must affirm that since the time of Archimedes there scarce ever met in one man in so great a perfection such a mechanical hand and so philosophical a mind. So, the idea in some sense of micrographia had come from Wren, but they were friends, and so Hooke could write something friendly about it. Now, of course, if you go into the modern age, there is an important development. So this is Heike Kamerlingh-Onnes, who's the person who first liquefied helium in the early part of the 20th century, and then went on to discover superconductivity. And one of the key things about why he won the race with Dewar is because he had an army of technicians, and here is Onnes with his head technician. And of course, this is something about modern science. It's much more collaborative. You have technicians, you have other people you work with, rather than just the lone individual working by themselves. You have teams of people. And one of Onnes's great gifts was not only that he was a good scientist, but he could work with other people and achieve great things. And that's something that is, I think, crucial about the development of modern science. Do feuds still exist? Well, yes, they do. So one feud that is going on at the moment is the question of room temperature superconductivity. Superconductors were discovered in 1911. It was a very low temperature phenomenon. Throughout the 20th century and the early part of the 21st century, the temperature below which you can see superconductors working, the so-called critical temperature, has been increasing year on year pretty much. But had got stuck at around 150 degrees above absolute zero. More recently, in the last few years, it's been possible to pressurize materials and achieve much higher temperature superconductivity. And a couple of years ago, in the journal Nature, room temperature superconductivity was reported, and this was seen as a great breakthrough. But there has been a huge dispute about it, and a few months ago that paper was retracted from Nature, and there is a dispute between two individuals, one who is criticizing these results. So disputes continue, and disputes in many ways are a good part of science because it's how science advances by examining ideas and testing them and working out what is true. But it is nice when they're not hostile and when there is a friendliness and a generosity of spirit. So I think in that point, as we conclude today, I think it's important to remember that though feuds can sometimes allow ideas to progress, it's always nicer if people can do so more collaboratively and in a more generous spirit. So I'll finish there. Thank you very much.
Thank you very much for fantastic closing summary talk, also perfectly in time. I think we would like to take just one or two very quick questions if there is displayed. Very briefly, please, the gentleman in the front, the third line. There is no microphone.
You mentioned about the sort of action at a distance for gravitation. How is that resolved for magnetism? So there was magnetic ball that was occasionally effects.
Yes, so with magnetism and electricity, the way in which we now would describe those forces being transmitted is by the exchange of virtual photons. So once again, there is a...
How did the Greeks deal with it? Because they had occasionally access to magnetic ore, and they studied it. They probably...
Well, so the way the atomists did it is by atoms. So there are little atomic particles that go from one magnet to another, and they cut the air, and they push the air out, and then the magnet is attracted and goes into the void. So yeah, you can read about this in Lucretius on the nature of things. It's beautifully done, and they have a mechanism for the whole thing.
Another display come. Just briefly, please.
What was the initial dispute between Wren and Huygens?
Between
Wren and Huygens.
Oh, so it was essentially a priority dispute. So the thing was, Wren had published his account and Huygens had published his account. And of course, there had been letters circulating. And I'm not an expert on this period, so I'm sure there are others who can say in more detail. But I think it essentially came down to, oh, in some letter, my ideas got leaked out. So it was the standard thing we were hearing about earlier today with conspiracy theories. You feel you're the only person to have had an idea. And it wasn't on Wren's side, it was on Huygens' side. But once they met, it was all fine. And Wren was immediately generous, as you could see from that quote about saying, well, Huygens' idea is better. I stand back.
But how did they settle the argument about priority?
Oh, well, essentially, Wren just abandoned his claim because he said, Huygens' idea is better than mine. My idea evaporates, which is how things should be.
So I would like to thank very much again for the summary. And also to Joe for organizing this fantastic event today. Many thanks for this.